This is the sixth video in the series about how to design a CPU. In the previous video, we learned how to create simple 1-bit adders circuitry. In this video, we'll learn about a tool called Karnaugh maps that will help us figure out more complex circuit design. From time to time when doing logic design, we run into digital functions that seem to be strange, and we need to figure out the circuitry.
So strange.
In 1953, Maurice Karnaugh came up with a way to do just that using something known as Karnaugh maps, or K-maps. The explanation for how Karnaugh maps work is a little confusing, but we mustn't let that scare us off. We'll work through a few examples to clarify how to use K-maps. Once we understand how they work, they are really pretty simple and very helpful. Karnaugh maps work by creating a table a bit like our truth tables. We can then use these tables to help us identify the algebraic formula that represents the function. Given the algebraic formula, it becomes relatively easy to convert the formula into a schematic. Let's work through some examples, and then we will use Karnaugh maps to figure out what the schematic is for the carryout function from the previous video about ALU adders. If you haven't yet watched the previous videos, that's not a problem.
You'll need to watch 20 hours of cute puppy videos.
In this video, we'll focus on how to use K-maps. Later, if you want, you can watch the other videos to see how to use Karnaugh maps to help you design an ALU. For our first example, let's imagine we have a simple function with two inputs, but we aren't sure what the function is. The function might have a truth table like the one shown here. In order to figure out the algebraic formula for this function, we construct a Karnaugh map. Karnaugh maps are always two-dimensional tables. These tables represent some of the inputs of the function along the vertical axis, and the other inputs along the horizontal axis. Here's a Karnaugh map for this first example mystery function. The top left cell of the Karnaugh map is a label that tells us that the far left column represents input A, and the top row represents input B. The shaded cells of the map represent inputs to the function. The non-shaded cells of the map represent the outputs for the combinations of the inputs. So, for example, the cell in the middle of the map represents the result when input A is 0 and input B is 0. The cell on the far right of the middle row represents the output when input A is 0 and input B is 1. The cell in the center of the bottom row represents the output when input A is 1 and input B is 0. Finally, the cell in the bottom right represents the output when both inputs A and B are 1. Next, we look at the patterns of ones in the output area of the map. To find a pattern, we want to circle as many contiguous ones that are in a matrix formation, such that the dimensions of the formed matrix are a power of 2, like 1, 2, 4, or 8, for example. That may seem a little hard to digest, but follow these examples and you will get the hang of it.
I think I'm getting the hang of this.
For this map, we will circle the output cells in the middle row, where A equals 0, and we also circle the center column, where B equals 0. Here's what it looks like once we have circled all the ones. Now we look at each of the patterns we have circled and we describe the patterns in terms of their inputs. In this example, we have two patterns, a horizontal group and a vertical group. We can describe the horizontal group as not A, since A is 0 for all values in the group. Similarly, we can describe the vertical group as not B. To complete the algebraic formula, we OR the two patterns together to form not A or not B. Next, notice that we can refactor this expression by using De Morgan's law to get A NAND B, which becomes very easy to convert into a schematic. Here's the simple schematic. Now, let's look at a function that is a little more complicated. Consider this truth table for this second mystery function. This function seems to have no discernible pattern, so let's apply a Karnaugh map to it. Remember that Karnaugh maps are two-dimensional. So, how do we create a two-dimensional map when we have three inputs? Well, one of the dimensions needs to represent more than one input. Here's what this Karnaugh map should look like. Each row represents a combination of A and B inputs, and each column represents the C input. By organizing the map this way, we can represent all possible combinations of inputs in a two-dimensional table. It is important to note that the order of the A and B inputs on the vertical axis is significant. The value of the A and B inputs must only change by 1 bit from one row to the next. Hence, the two inputs do not follow a normal binary counting sequence. For example, 1, 1 follows 0, 1, instead of 1, 0 following 0, 1. As we did in the previous example, we now need to circle the patterns of ones. Remember that we want to circle as many contiguous ones as we can, such that the number of rows and the number of columns of the circled pattern is a power of 2. As we circle the patterns of ones on this Karnaugh map, there are two things to keep in mind. First, the patterns can wrap around the map. In this example, the cell in the top right may be combined with the cell in the bottom right, but we cannot combine the cell for the input value 111 into the pattern with the other cells on the right, because that would not create a pattern with a height that is a power of 2. However, we can create a second pattern that would consist of the cells based on the inputs 110 and 111. Second, we only need to create enough patterns to cover all the output ones. In the example, we could create a third pattern based on the inputs 111 and 101. Although it's okay if patterns overlap, in this case we do not need to create this pattern because the other two patterns already cover all of these cells. Here is the circling of the patterns we will use to create the schematic for this function. To derive the algebraic expression, we look at what inputs remain constant for each of the patterns. For the horizontal group, this is A and B. For the vertical group, this is not B and C. Then, as we did in the previous example, we OR these two expressions together. Just to be clear, this expression maps directly to this schematic. Now, let's return to the strange carryout function from the previous video and see if we can use a Karnaugh map to figure out the algebraic expression and its schematic.
Where? Back to the future.
As a reminder, here's the truth table. And here's the Karnaugh map we create from that truth table. We have to use 3 circles to include all 4 ones, which means we will have 3 algebraic sub-expressions which we will OR together. The horizontal grouping represents A and B. The upper vertical grouping represents B2 and carry in, and the lower vertical group represents A2 and carry in. When we combine these groupings with OR, we get this expression. We can refactor the carry-in to simplify the expression to look like this. We might be tempted to convert this expression into a logical schematic, but not so fast. We can do a bit of an optimization and take advantage of some previous work. Recall that the schematic for the output 2 column is an XOR function for inputs carryout and A2 and B2. Is it possible that we could use this calculation to calculate the new carry output? This optimization is not immediately obvious, but people have been working on adders long enough that they have discovered this reuse of the XOR function. Rather than fight our way through a proof, let's use Venn diagrams to quickly and intuitively understand how we can use this XOR optimization. Look at these 3 diagrams. The diagram on the left represents the expression of A2 and B2. Notice that this expression is the first term in our Boolean expression we derived using the Karnaugh map. The middle diagram represents the expression carry, ANDed with the quantity A2 or B2, which is the second term in the Boolean expression. The rightmost diagram represents the expression carry, ANDed with the exclusive OR of A2 and B2. Now, imagine ORing the left diagram with the center diagram, which basically means that we would overlay the diagrams. Notice that this result is the same result we get when we OR the left diagram with the right diagram. So in this case, we can replace A2 or B2 with A2 exclusive or B2 and get the same result. Since we already have to calculate A2 exclusive or B2, we can just use that result instead of creating additional circuitry. We can reduce this resulting expression to a schematic that looks like this. Now, we are armed with all the parts to complete the 2-bit adder. Here's the schematic. In the next video, we'll show how to generalize this work to n-bit adders. Subscribe and click the notification bell so you can be notified of future videos.